Recording.
Yeah. Good morning, ladies and gentlemen, or good afternoon. So, we're starting off on the second set of notes. I think we're about, I don't know, a couple pages in. And we left off talking about the plate heat exchanger, and we were giving you an example of a plate heat exchanger. Shell and tube's not suitable for small holdups. Transfer is fast, suspended solids, so there are limitations into shell and tube. As you should know, in design, there's limitations and there's advantages versus limitations and all this. Here's a picture of our plate heat exchanger. And I was saying I wouldn't own one. If you don't open it up, you're going to keep it on, don't clean it, say for 10 years, this would be a great piece of equipment. However, you got to recognize there's significant gaskets in here. And once you open it up, you have to buy a whole new set of gaskets. And it's quite a challenge to re-gasket this thing. Number one. Number two, since there's gaskets between each plate, I often say that this heat exchanger is a gasket. The heat exchanger is limited by the properties of the gaskets. Heat exchanger has to withstand certain temperature ranges and certain pressure ranges. And as a result, the gaskets have temperature and pressure ranges in which they work. And that limits this heat exchanger. Old gaskets never reseal. You probably know that. And every time you open this thing up, you have to, as I said, regasket. Regasketing the gaskets themselves cost 30% of the original cost for the heat exchanger. So obviously 30% every time you clean it makes this a heat exchanger that you don't want to have around that much, right? So my recommendation is don't use this heat exchanger. Okay. Let's see if we can get actually this thing to work right for a change. It's not working right. So we go around. It's not working at all. Anyway. So let's see here. What do we got here? Apparently it's not reading a page, and it's not reading counterclockwise or clockwise. Pretty disturbing, huh, gentlemen and ladies? Wait a minute. We first page here, second page here, and now we got our problems here. How do we get this to be rotated back? And we see that technology fails us again. Simple request. It doesn't work. So what do we want to do here? We want to go back to this thing and reopen the notes and see if we can open them up again. So let's see what we run them down through here. See how far we go until we... there we go. We got this. So one that we were looking at before, and now we continue on. Now, I used to think APV was aluminum paint company, aluminum plant and vessel company. Maybe that's what it was. First commercial design was 1923. What is plate exchanger? Like a plate and frame filter press, if you know what those are. Advantages: easily assembled and disassembled. Cleaning is easy. Meets most stringent sanitary and hygienic requirements. Heat transfer is changeable. You can add more plates. It's very important. It's high turbulence, high heat transfer. A lot smaller area than shell and tube because it's a lot better in the way of heat transfer. It fouls less as well. It's higher velocities and less fouling. So let's see here. Velocities are low. Low temperature approach. Delta T log mean temperature difference is fully used. Leaks usually to the atmosphere, not to the process. Bad gaskets can be changed. Again, as soon as you open it up, old gaskets never reseal. Low hold-up volume is an advantage. Costs, lower costs, lot less material in here. You're looking up around 300 psi. Now you can also weld the plates shut, so you could possibly go up to 1500 psi. Gaskets usually go to 175C or 260C, depending upon exactly what it is. Yes, asbestos gaskets do exist. That's pretty hot, and the pressure of 300 psi is pretty high pressure, so those two conditions make it quite versatile heat exchanger for low pressures and temperatures. These are pretty high temperatures, and high temperatures somewhat. Velocities, well, 0.1 meter is pretty slow. Average velocities, you're looking for about 2 feet a second. Gas service, due to high pressure, includes duties and low pressure. Clogging occurs easily in plates. You don't want that. Suspended solids should be less than 1/2 the corrugated depth. You're always worried about solids in the flow. High pressures, plates deform, gaskets fail easily. Now, obviously, you need to pay attention to gaskets. Now, to buy one of these plate heat exchangers would be horrible, because every time you open it up to clean it, you got to buy a new set of gaskets. Now, the person selling the plate heat exchanger really loves you, because when you buy a plate heat exchanger, that means you'll have to be purchasing gaskets in the future, and he gets 5% of the cost of the new gaskets. Got it? He or she made 5% on the sell, maybe 10% on the sell of the heat exchanger to you. This is what I would call equipment rep. And when they sell you a piece of plate heat exchanger, they're looking for further income in the future when you have to rebuy gaskets, repurchase new gaskets. So from their perspective, it's very advantageous for you to buy a plate heat exchanger. From your perspective as an engineer, not so much, right? Plate heat exchangers have their own fouling. Here's another picture of a plate heat exchanger. And fouling factors, different fouling factors. And you can see this has sort of been updated, 1983. Don't use shell and tube fouling factors, right? Fouling factors is a function of your process, number one. And it's also a function of the equipment used in your process. So fouling's tough. It's a little difficult. Fouling in plate heat exchanger, about 1/5 that of shell and tube. Few stagnant regions, high turbulence, low residence times, less chance to foul. Erosion, corrosion is 2 mils a year. The plate are usually 20 to 40 mils thick. So after about, I don't know, say 10 years, your plates may be disappearing on you, which I haven't really thought about, right? 2 mils a year, maybe 20 mils thick is the minimum. So 10 years here will knock this 40 down to 20. Ooh, that's not good. Usually what will also happen is corrosion will be localized. So 2 mils a year may be an average. You may have spots in the plates where there's higher corrosion, in which case the vendor will really love you. Erosion occurs from overcapacity use in suspended solids, occurs over the entire plate. So you use erosion resistance material. This is a dream picture of the corrugations in the plate and the flow field that's going through there. You can see you have a contraction and expansion. You have tumbling vortices in there, and that's the reason why you probably have a higher heat transfer. Now, this right down here is multiple duties. Oh boy, if you buy this thing for multiple duties, you can consider yourself stupid. I mean, you know, this is, how can I say this? This is just asking for it. I mean, come on, man. Think a little bit. For example, I have this heat exchanger. I have to take down this heat exchanger because it's heavily fouled. But because of the stacked nature, I have to take down this process, and I also have to take down this process. This ain't a good thing to have. This thing down here says multiple duties. See the word don't? What you want to do is have one plate heat exchanger for one job, another plate heat exchanger for the second job, and the third plate heat exchanger for the third job. It's called the KISS principle. Keep it simple, sweetheart. Right? I'm always amused by stupidity that's published. I find this quite interesting. You know, there's a lot of stupid stuff out there. And not only that, they actually sell it. And not only that, some people think it's best thing since sliced bread. What happens is you give two different people the same piece of equipment and ask them to write a performance review on it. And what will happen is one group of people will think, hey, this thing is best thing since sliced bread. And the other people will write up a report saying, this is a piece of trash, get it the hell out of here. Same piece of equipment, two different evaluations. The evaluations do not agree. Sort of like the Democrats and the Republicans. You know what I mean? God almighty. And they now are shooting each other. Did you see that? Yeah, we better get the armed militias up. Anyway, just kidding on that. Just kidding. Now, Dan, what happens is I would rotate this for you, but since I'm somewhat delinquent in my capabilities, let's try that again. Let's rotate it. We'll take a chance here, gang. Pressure limits, temperature limits, flow rates, gaseous flows, high viscosities. Look at that, plate heat exchanger is preferable. Flow maldistribution, this is spiral. Flow maldistribution is possible. Yeah, there you go. Heat sensitive stuff, you know, there are things that are heat sensitive. Heat recovery, all kinds of little items over here. And there are three different designs, plate, spiral, and shell and tube. And here, oh, excellent. Continues on this thing. I forgot to mention that. It's this is I had table 6.2, great table, making a comparison between heat exchangers. This is absolutely wonderful, and you got some more there. And then you got this thing that we're going to try I guess we got to click on it, maybe, and then rotate it counterclockwise. That ain't working again either. Okay. So apparently we have another malfunction, so we just get rid of that thing right there. Uh-oh. Let's bring it back up. Nope, can't bring it back up. There, we bring it back up. So what do we want to go? We want to go back here, and we want to hit this one more time. So we always have since obviously we have a problem here, we get rid of that one, and we get rid of that one. So we're back to square one, and I guess this is the way I have to operate. So we went through the comparisons. Those are wonderful comparisons for you, right? There they are. Wonderful items. Then we talk about maintenance, inspection, and cleaning here. And you see basically students want an A. Okay, A is very good, B is acceptable, D is impossible. So if I take a look at a shell and tube exchanger, I ain't ever going to be able to expand that. And over here, I have a spiral. I can't expand that. But in this plate, I just add more plates. And you look at all the A's over here for this plate. And then the leakage inspection is B. So they're apparently in a really nice attitude towards plate heat exchangers because they went to sell you one. Now over here you got a combination of D's and B's, and over here spirals. So cleaning, to be quite blunt with you, chemical cleaning, AA. Corrosion inspection, I would have to claim AA on that. I don't know why. Leakage inspection, I'm sorry, but that has to be AA, and this has to be AA, because we haven't really talked about spirals. You know, I wouldn't trust these guys down here. See this? I wouldn't trust these. Because spirals are really great heat exchanger, don't get me wrong. And the C down here for repair, I don't know. This is an evaluation of different things. Relative cost, yep. You make everything out of Hastelloy. Look at that, factor of 8 over stainless steel rubber gaskets type thing. So it's always nice to know the material you're going to use and how much it's going to cost. And okay, typical dimensions for a plate heat exchangers given there. Heat transfer coefficients, look at that, 500 to 1,000 BTUs per hour foot squared degree F. There you go. That's good stuff right there. Remember, shell and tube, this was maybe 30, 60. 300 was pretty good. Velocities, 3 meters a second, not 10 feet a second is typical, right? 1 millimeter thick. That's pretty lightweight stuff here, gang. Materials, you have seawater, titanium. With chlorine, titanium. What you don't want to have is chlorine and stainless steel. That's I got chlorine solutions with stainless steel. I'd be careful. I thought chlorine and stainless steel didn't go well together. That would be probably a test question. Gasket materials, remember, this sets the limits on your heat exchanger. By the way, you'll have these notes for yourself in the when you take the exam. So what I would probably do was, what gasket material would you not use for fats, right? Or what gasket material would I use for oils? Well, there you go. Silicon rubber limited to sodium hypochlorite and low temperatures generally. There you go. Anyway, you got the material, gasket material, you got asbestos, and you can see that asbestos goes to 260 C. The rest go up to about 150 C, 300 Fahrenheit. Anyway. Corrugations, right? Break up the boundary layer, determine heat transfer and pressure drop, greatly increase or decrease heat transfer coefficient. HTC is heat transfer coefficient. Thermal performance is determined by corrugations. Now, they go into a big thing about corrugations. Whenever you see a V like this, right, a V, they call them chevrons. One set of V's, it's called chevron. Sort of like the company, Chevron Oil Company. So this would be a long duty hard plate. This would be medium duty medium plate, and soft plate duty. And obviously you can see there's a lot more corrugations things than happening over here, right? What is the differences between this and that? And you can see whatever these crosses are, it's much smaller over here. And I get the impression that there is more lines, more corrugations per inch here than over here, right? Anyway. I have no idea what this is. I don't like heat transfer units. You might get, typically you want the log mean temperature correction factor to be above 0.7. So you want to maintain it above 0.7. Flow in a pay, you have spiral, loop, complex flow designs. Basically, what do we got here? Here's a design sheet for you. All right, let's go back here. Let me explain how you design these things. You just go to the company who makes these things and say you need this, this, and this, and they will do the design for you. Shell and tube design information is out there in the real world. As I said, if you do computers design of shell and tube heat exchangers, you're probably using some version of Bell Delaware. Okay. However, nobody was heroic and published information about plate heat exchangers. So a lot of the information about plate heat exchangers is proprietary. As a result, you don't have any information. So you just turn it over to the company and let them do the design for you. Design sheet. All right. I suspect that if you looked at the correlations, pressure drop and heat transfer coefficients will be similar to shell and tube heat exchanger. Leading coefficients will be different. That's the proprietary nature of those. The exponents on those will probably be different as well. Wide variety exists in equipment and applications. Physical properties are fairly constant. Okay. Correlations are known for laminar, turbulent, non-Newtonian. High turbulence, great thing, great items. Low resistance, easy cleaning. Low fouling resistance, doesn't foul. Thin plates and the heat transfer coefficient typically there. Now a shell and tube, this would be maybe down around 300 or less. That's BTUs per hour foot squared degree F. Design, this is kind of a funky design method. I wouldn't bother. And here, I think this is what your book actually uses, a number of heat transfer units, if I'm not mistaken. But I would, like I said, you just go talk to the vendor and have them do the design for you. You don't want to play hero. Playing hero often gets you killed, right? So you become vendor dependent, and that's okay, so long as the vendor is capable. In which case, you should try to do vendor testing. I don't know if you realize it or not, but they're just ordinary human beings, and you can have them take tests. Maldistribution, this is a major problem. Flow maldistribution occurs everywhere. Major problem in industry, everywhere. Flow is not going where you want it to go, and hence we call it maldistribution of flow. Occurs in particular with high viscosity fluids. Now, when I say high viscosity fluids, that really means high technology type fluids, the things that matter. It usually happens with low and high flow rates. And in this case, for heat exchangers, plate heat exchanger, it happens for long plates. And trapped air bubbles or trapped gas bubbles in liquids is not uncommon. And also due to different pressure drop differences in manifolds. I bet you don't know what a manifold is, do you? So we'll make that a test question. Tell me what a manifold is. Maldistribution affects heat-sensitive materials. Now, what is a heat-sensitive material? Most everything will burn, so most everything can be heat-sensitive in some degree. It's a matter of how much heat-sensitive it becomes. Good point of doing heat sensitivity is perhaps cooking. Heat-sensitive materials, food often burns, so obviously you've reached the heat sensitivity nature of that fluid. I suppose if you're making scrambled eggs in the morning and you scorch your eggs, it doesn't look good on the plate. That's heat sensitive material, right? Okay, other applications might be vaporizers and condensers. I don't know about that. Climbing film condensers. There's no volume in a plate heat exchanger, so I don't know if I. Anyway, let's go on to spiral heat exchangers. This is fantastic. So your assignment is I want you to go to the grocery store and I want you to buy a jelly roll. And you will notice a jelly roll will look like this right there. And this will be a spiral heat exchanger. And what happens is fluid comes in. Just take the fluid coming in and the fluid exiting. They have a channel. So the white fluid is coming in, going around, around. So the white fluid comes in here, and the darker fluid goes around. I guess the white fluid is going the other way. Sorry, white fluid is coming out. So the white fluid comes in, spirals around this way, and then exits here. The black fluid comes in here and spirals around, and exits somewhere. Anyway, that's a spiral heat exchanger. And all they do is they take two plates and put it on a mandrel or put it on a shaft and they rotate it. And as they rotate, they wrap different. They put in spacer studs and they continually wrapping the heat exchanger around itself. So let's see what we got here. We should also say that this channel may be open for cleaning. If this channel is open for cleaning, that means it's welded shut down here. So one side of the channel is open, so you can clean it. This channel, since this one's open, this one's welded shut. So by having a very welded, unwelded, welded, unwelded, right, they can keep the fluid separated. Channel cover fits on top of this thing. These spiral heat exchangers are pretty much everywhere. There's different ways of operating them. You can operate them as a total or a condenser. Say you add a distillation column, you can put it on top of distillation columns. This thing right here is a condenser, right? Vapor coming in, being cooled by the darker fluid and collapsing here, and the excess vapor goes out the top. Or potentially you could have something looking like this. Now I guess that would be a, see, the fluid coming in is exposed to all these spirals here. They're not counter spirals. So up here they're counter spirals, right? So this is a regular shell and tube. And let's see what they call the other ones. Spiral, spiral, spiral cross flow, spiral flow combination, spiral cross flow. This one's quite complicated here. You have the spiral flow here, then you have cross flow here, but then you have the exit over here, so spiral cross flow. One major manufacturer, there's 3 or 4 actually, one major manufacturer is Alfa Laval. And so I want you to go on YouTube, type in Alfa Laval and see if there's got any YouTube videos for you so you can watch the YouTube videos. Alrighty. So fouling deposits are low. This thing can handle lots of slurries and large particulates. In other words, it would be very good for a strawberry jam with large chunks of strawberries in it, no problem. Fluids are can be always in countercurrent flow, which is wonderful. Log mean temperature difference fully utilized, except cross flow. Close temperature approaches can be reached, and if I was taking this course, I would raise my hand and say, Dr. Tatterson, what's meant by close temperature approaches? That way you are less susceptible for me to not ask that question. If you don't know the answer, don't blame me. Small sizes, easily mounted, HTC, heat transfer coefficients high. No leakage, low maintenance, easy maintenance, great, that's true. No large thermal expansion. If it expands, then expands differently. And of course, we have the three different types here that we already showed you. Applications, well, 50% weight by solids. That's pretty good. Heavy filing fluids, that's good. You have condensation, that's good. Gas cooling and heating, that's good. Yeah. Lots of applications, lots of applications. For those of you in the mechanical engineering area, you should recognize that chemical engineering companies, the petroleum industry hires an awful lot of mechanical engineers, right? So you shouldn't poo-poo. Anyway, expensive. Be expensive as a shell and tube. Pressure limitations. We said 300 psi. Well, maybe it's 250. It's practical. Temperature limits, practically none. Units have been built to 250 C. Yeah. Of course, that's a function of the gasket material. Area limited to 250 square meters. HTC is 500. That's pretty good. Not good for thermal cycling, right? Not good for cyclic temperature service. Unless metal gaskets are used. Expansion, contraction grinds ordinary gaskets. That's true. Gaskets never reseal. Let's see what else we got. Now. Exchangers with phase changes. There you go. Vapors, liquids, evaporators. By the way, the power industry also hires a lot of mechanical type people. You know what I mean? Refrigerating, power plants, making gasoline. Anyway, we're not going to talk about gas-fired heaters. Requires an understanding of radiation heat transfer. We'll get to that understanding a little later, but we're not covering them. Magnetic heat exchanger. I love this device. What happens is this is a pipe inside of a pipe, and it's capped off. So the flow comes through the center pipe here, and then comes around and exits right up through there. So there's sort of an annulus formed. And what happens is as it turns the corner down here, it boils off. So you have a significant boil off happening if it was designed well. And boiling will take away an awful lot of heat. Awful lot of heat, yeah. If you want to take away heat, boil. Okay. Yeah, oh, look at that. What do we got? This is a discussion of condensation. I guess that's what we're going into, right? No, I don't think. Anyway. Take a look at what we have. Classification according, this is for condensation. All right, so we have two major groups of people that are involved with condensation. One would be power industry and chemical process industry. Dropwise condensation doesn't happen, so you're left with filmwise, where there's a film, a liquid formed, and direct contact condensation. There you go. Example of a direct contact condensation, there's a big, huge tank up in Abbott Labs. Pharmaceutical companies employ mechanical engineers as well. Anyway, this big 10,000-gallon reactor, as big as this room, right? Whatever room you're in, this tank was as big as what room you're in. So we're not talking small. And it was filled with a really hot steam, okay? And this one particular engineer comes in and turns on the cooling water spray, the hot steam, and a big tank. So what that means is you had significant condensation of the steam involved. So that created a huge vacuum inside this tank. And when everything finished and they finally stop this stupid process. The tank looked like a Coke can that had been crushed in. Anyway, so you have different extent of condensation. You have de-superheater condenser, partial condenser, total condenser. You have to see de-superheat means it's colder than the boiling point, or higher than the boiling. Higher, could be both ways. Superheat, you got to recognize what superheat means, and then you take out. It's the de-superheating, right? So maybe I have a lot of hot steam. The steam will condense at, say, whatever, 200 degrees C, but it's at 250 degrees. Condenses at 200 degrees C, and the stuff is at 50 degrees, 250 degrees. So it has 50 degrees of superheat in it. So you drop the superheat down to the condensation level and condenses. So there's two things involved. You do the condensation and you also do the de-superheating. Condenser and subcooler, there you go. And then you can have the de-superheater, and then you have the condenser, and then you have the subcooler. So, anyway, kind of interesting. Only on film-wise and direct-wise condensation. And here you go. And you got the three choices shown: tube, plate, and spiral. And if you were in Saudi Arabia, you would also worry about air-cooled. And we have the pure vapor. Say you're condensing water, that's a piece of cake. Now over here you have one hell of a situation where you're condensing materials that are miscible. You throw in a bit of non-condensables in there, and then you throw in a fluid that's immiscible. So think of it as you have a mixture of water vapor with an organic oil and air, all hot, coming over. So you have water. Actually, let's reverse that. Water would be the immiscible fluid, and then you have 4 or 5 organics in there, which would be the miscible fluids. So you have a real mess on your hands. This is fairly easily done. Pure vapor is not hard at all. This is, there's very good design methods for pure vapor. There aren't very many good design methods for, this is a challenge. What you do is you build one and see how it works, and then since it works so well after you've been building them a lot, you use that as your standardized design. And then we have vertical and horizontal condensation, inside or outside tubes. We have gravity controlled. This is natural. And we have shear controlled, which means there's a pump or some sort of prime mover involved. Dropwise condensation doesn't happen that much. Small drops are formed. So I got a little experiment for you to do. It's not going to be very hard. I want you to take a key and a pop out of the ice box. Now you got some soda in the ice box. I don't know whether you want to call it a soda. You don't know whether you want to call it a pop or you want to call it soda pop. It's carbonated water with a little bit of coloring and perhaps artificial sweetener or that terrible stuff called sugar. So I want you to set it on the countertop, and I want you to observe the dropwise condensation that occurs. It's a very faint covering. Looks like dust. Basically, the drops do not combine. They stay. No films form, no added resistance. Condensing surfaces have to be specially prepared. Well, if you're taking it out of the icebox, it's not that specially prepared. Okay, gold Teflon waxes help. Doesn't happen in the plant environment. And typically you'll be having fouling occur, and that will cause you to have condensation. Preventing fouling, there you go. Now, film-wise condensation is another matter. Basically, it means there's a film formed. See, film-wise, it's film formed. Drops condense, form a layer. Liquid wets the surface. Heat transfer has to pass through the condensate layer. You can have higher heat transfer resistance, lower. So what we have here, I really like this picture. It's a fantastic picture. And since it's a fantastic picture, this rotate it. What we have here, we got to look at this diagram over here. We have a pipe, and the pipe is designated by this thing in here. Okay. So we have a film that's occurring on this horizontal pipe. It's a horizontal pipe. And so you have film built up, and it's the thinnest at the top, and the gravity causes the film to come down here. So you got a picture of a falling film here. Film thickness is shown by this curve here. And then you see the heat transfer curve, which is going this way here like that, up here. So the highest heat transfer occurs at the thinnest film thickness. The lowest heat transfer occurs at the biggest thickness. Vertical tube, there you go. You have, on a tube, you have the liquid loading building up. We call it loading, right? Loading, liquid loading. It's how many pounds per second that's dripping off this thing divided by the perimeter of the tube. So you see as the film gets thicker and thicker and thicker, the heat transfer coefficient drops. Okay, the film forms but accelerates, and so kind of an interesting phenomenon. We'll get to more of this in the when we go talking about condensers. And I see we have our same problem here, so we'll go back here. We're at page 39. Voila! So let's see what we got here. We can only rotate once, then we go to hell. When things don't work out for you one way, then you're just going to have to beat the system, you know what I mean? When you stop one way, what are you going to do? Roll over and play dead? No, you just get up and attack it a different way. Okay, so there you go. Direct condensation, right? Direct contact condensation. Subcooled liquid sprayed into vapor. Spray towers used, good method for condensing. Very high heat transfer coefficients. No surfaces. You have no surfaces in this thing to foul. So there's no fouling, no material barrier. Little thermal resistance, right? Operating costs is no tubes, no surfaces, no pressure drop. Use limited but fast growing. There you go. Smart things actually rise to the top. Maybe. Unless you're surrounded by dummies. Anyway, give you an idea what that looks like. Uh-oh. Let's go ahead and do it. Anyway, you find the liquid coming in, a curtain, liquid curtain, falling down another liquid curtain, a tray of liquid, another liquid curtain. So if I have vapor in, the vapor has to go through this liquid curtain. It's called a waterfall in nature. It's really, it goes through that and that and that and that. And by the time it comes out, it's fairly well condensed. Or over here, you have vapor coming in, hitting a stream of very cold water and condensing out most of the perhaps steam that's coming in and venting the non-condensables. All right. So we know that we're going to fail at this in the counter rotation. So we go back to this and ask for a new set of notes there. I guess we're on page 39 or whatever. So we clobber that one and we go to page 39. Oh, and there's page 41. Experience? Even pure vapors will have non-condensables. Need to know the concentration levels. Very small amounts can build up. It can have adverse effects on performance and need to purge. So what do we got here? Let's see what else we got here. Possible design, shell and tube most used, plate not used much. Remember, you need large volumes, I think. Large surface areas. Small surface areas needed, broad flow passage required, less likely to clog, air-cooled designs out there. There you go, there you go. You have a loop seal. I hope you understand how a loop seal works. Any liquid that's up here will fall over due to gravity, right? You know, gravity works this way. So the liquid in this tube would be right here. Anything more would flow over. So what that means is the liquid inside here is the same level as that right there. That's called a loop seal. You have these everywhere in your bathroom and kitchen sinks. Basically, this part is sealed with, here it is, your bathroom sink here. Basically, this is a loop seal, right? The loop seal is not here. The loop seal is right here. You see the loop? And what the loop seal does, it prevents stuff from coming back up. And science horror movies, you got those snakes that come out of the toilet, or you got the rats that are coming out of the toilet. They have a tendency not to want to enter the water or liquid here. And that's why you keep the bad things in the sewer system here. Also, anyway, this stuff could possibly be condensate, subcooled condensate. Condensate's really tough to pump, right, because it's near its boiling point. We got the loop seal over here, right, same sort of idea. And then we have a standard view of a condenser. Vapor coming in, these are supposed to be baffles. Vapor coming in, you got a bunch of tubes in here condensing it out. So there's a modest decrease in flow here, going across that tube bundle. Some more decrease in flow here, going across this bundle. So as you're going down this condenser, there's less and less gaseous flow because it's all being condensed out, right? So you got perhaps exit nozzle here, perhaps. You may have a throw in a vent to get rid of the non-condensables. Oh, there we go. There's some more stuff there. Vapor belt, what the hell is this? Expanded nozzles, we already covered that. Loop seals, we covered. We never did figure out why baffles are notched at the bottom. Various methods for calculating heat transfer coefficients for condensers. If you look, there's Nusselt, Colburn, Kearns, Duckler, Ward's, Bell and Gainler, and Butterworth's. So you got a number of ways of doing this. Emerson's method available. If you look up here, widely used for multi-component partial condensers, accounts for cooling a condensate, condensing inside and outside with and without temperature, without vapor superheat. So this looks like really hardcore stuff. Put hair in your brain. Now down here you have probably another method as well, accounts for the variation of HTC along the condenser. don't want to hurt your all's feelings. It's difficult for a design method to account for everything. All kinds of situations arise, require special treatment. Got to realize that the person using the equipment how can I say this? It may be doing things that wasn't anticipated in the design. So you got a design sitting out there, and the person uses it in a different manner than what it was designed for. This occurs often, right? Condensation over two bundles, differently for horizontal and vertical. Real problems. Okay, maintaining equal distribution of material. There you go. This is the flow maldistribution problem. Unequal distributions cause unequal heat transfer. Unequal transfer causes unequal distribution. Unequal fouling causes unequal heat transfer and material distribution. Unequal heat transfer and material causes unequal fouling. They're all sort of in there together. Here we have a pure vapor sitting here. We have the metal wall, and we're taking away the heat with another. So it comes and condenses on the film. This is a film condensation. Now when we throw in non-condensables, so we still have the liquid films there, but now we have a diffusional layer that's sitting here. Because we're trying to condense steam, but the steam has in it air or oxygen. Steam and oxygen condense at way different temperatures. And so what happens is the steam will condense, but leave behind a layer of oxygen, and that layer of oxygen or air will be sitting right at the surface. So this is no problem. No problente. This is a big problem. So what you need to do is have a situation. You don't have to accept it, right? You're going to have this problem, but you don't have to accept it. So you keep this surface disturbed, basically. You don't necessarily want to disturb your condensation layer, but you do want to have since this is vapor, you do want to have a strong breeze across the condensation film so that you can get rid of that diffusional layer, right? You don't want this to happen. You want to get rid of this. This is gas. So, anyway. Condensation retention on fin tubes. There you go. What do we got here? We got large surface tension over here, and we have small surface tension over here. And then we have fin height. This is small fin height. And up here we have large fin height. So if you look at this, the fin's not very effective. The fins disappeared under the condensate level. This is the highest. The fin surface is exposed. This tank too hot right here because this and this are very similar to each other. So you're looking for a low surface tension, obviously. And we know the three things that affect surface tension is purity of the surface, the temperature of the surface, and electrical charge at the surface. Be curious to understand how electrical charge can affect the operation of a condenser. That'd be kind of interesting to worry about. Wouldn't it be funny if you went and took a 9-volt battery, which is basically harmless, and hooked it up to your condenser, and suddenly you got an improvement of 100% just because you put a little electrical charge on the water or the liquid condensing? Electrical charges do not like each other. I mean, positives don't like positives and negatives don't like negatives. So if I charge this surface with positive charges here or negative charges here, maybe the electricity is flowing this way, I could avoid this, or I could avoid that, or I could avoid this one. In other words, a little bit of electric charge can go a long way. Or, put it another way, a little bit of electrical charge can change your operation of your system. And I guarantee you, ladies and gentlemen, you know squat about electrical charge, right? You don't know. Well, when I say you don't know anything about electrical charge, you join the great masses of people who don't know anything about electrical charges and how they affect fluid mechanics. Right. So if you got something that's very odd happening and you don't understand why, there's a whole bunch of science out there that you don't understand yourself. So electrical charge is one of those really cool things that I personally am still learning myself. Anyway, electrical charge can wind up killing you as well. You haven't died from a 9-volt battery, no. But stop to think about it. I want you to go on the YouTube and type in gasoline stations, comma, static electricity, and type that in. Anyway, this could be static electricity or a static, this is charge right here. Go next time when you fill up your gasoline tank at a gas station, read the signs around the gas pump. Might save your life. Design of a condenser, you got many problems, right? Bam, 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 bam. Fogging is one. Presence of immiscibles, different flow regimes, mass transfer through the non-condensables, pressure drop. So, let's get real here, gang. What do you do? Well, got news for you. You're not gonna, you build the best condenser you can with the most versatility, robustness, nimbleness, ease in cleaning, right? You build the best one you possibly can. Right, and then you use it, right? You'll have some of these problems too, true, but you got the best exchanger or best condenser that you could possibly have, so you go with it because you ain't got anything better. That's how you do design when you don't know much. You go with the best equipment you can and hope for the best. Fogging. Fogging happens all the time in nature. Great Smoky Mountains, called smoky because of fogging. Anyway, it's not uncommon for condensers to have fogging involved. A whole bunch of problems, far more difficult than a heat exchanger design. Problem areas, yeah, fogging, there you go. One of the interesting things is about processing or whatever is you make assumptions and you think that's the way it's going to happen in your design, and it just don't happen that way. You know what I mean? Surprise! Lots of surprises in the world. All right? Can you imagine? Homogenization, homogenized condensation on my nuclei. Anyway, nuclei leaves with the purge, hopefully. Fogging is a good, interesting point. To avoid fogging, there you go. You didn't even realize fogging was going to happen. There's some design recommendations and suggestions. Ooh, look at that, some heat transfer coefficients. Look at that, superheat can be ignored. There you go, unless it's 25% of the total heat load. Condensing, you want to use vertical tubes. Actually, you don't want to use vertical tubes. You want to use vertical tubes with rims, so the liquid film will flow off the rim and expose fresh tubes. Fresh tube area for condensation. So you use impingement plates, vibration due to impingement plates will prevent erosion, that's very important, and also limit possibility of vibrations, right? Baffles should cause the vapor flow over the tubes. Baffles should be staggered, maintain equal velocities over the tubes. Baffles will prevent dead zones, direct vapor into the inlet outlets should be avoided. That's pretty funny. You got this very complicated inlet and exit are right across from each other. So you have this very complicated design. The flow comes in, leaves the exit, doesn't even go through the equipment. That's not uncommon. Vents should be located near the exit. Condensation not flow out vents for NC, non-condensables. You want the dirty stuff, hard stuff on the tube side. Exit nozzles should. Here's the condensation spec sheet. There you go. Other condensers here. There you go. There you go. We should cover that, I guess. Boiling we'll talk about a little later. Reboilers, right? We'll talk about that when we get to them. And that brings up the end of that. So we go back here and go to notes 3 and see what comes up. Boiling, different forms of boiling. This, for the most part, skip this for a bit. We may come back to it. But that will be Chapter 9 in boiling. Famous curve. This is kind of interesting. Let's just stop for a moment. You have liquid coming in here, and you have vapor coming out at the top up here. So you have very high density fluid and very low density fluid. And you know that rho VA equals rho VA. So you have high density, low velocity, and you have low density, very high velocity. So the velocity change in here can actually by a factor of 1,000. Comes in at 1 foot a second, leaves at 1,000 feet a second. What's the speed of sound? Does it form a shock wave? That's interesting. So I want you to recognize that there's a huge vapor expansion going on. Test question might be, what volume does 18 cc's of water have when it's turned to a vapor? 18 cc's of water as a liquid turns to a vapor, what volume is created? So you have a huge, basically what you have is the vapor explosions in here. Okay, so that just gives you an idea. I want you to pop some popcorn, right? Popcorn in a microwave. First off, you got to recognize microwaves don't necessarily heat uniformly. They heat from the outside in. So once you got your popcorn popped in those bags, I want you to pull it open and watch all the steam go off, right? It's very important to watch the popcorn steam go off. Now, I was a bit slack one time. I opened up the bag of popcorn and put my hand over the exit for that bag. I scorched my hand. I'll tell you, as bright as I am, I wound up scorching my arm. It hurt like hell for at least a couple of days. It was all red. It's like I was trying to cook my hand. Then I want you to go on YouTube and I want you to watch popcorn popping, right? Popcorn popping is much similar to this down in here. You have bubbles bursting. Popcorn, the reason why it pops is you got a little bit of moisture in the popcorn. Little bit of moisture in the popcorn. And essentially you have a vapor explosion inside the popcorn. And it's kind of cool to watch it. You can see a small little kernel turn into a huge popcorn kernel, or a popcorn particle, I guess. This type of stuff is really cool stuff you need to, how can I say, pay attention to. It's kind of cool. So that's your YouTube assignment. First assignment is pop some popcorn and watch the vapor come off. It wasn't there to begin with. That vapor was caused by the heating, the vaporization of water in the kernels. You should realize that a little bit of liquid water does an awful lot of popping. The kernels that don't pop don't have any moisture in them, right? So you're going to watch YouTube on popcorn popping, right? put hair on the brain, let you understand things a little bit more. Horizontal, first off, this is vertical. Horizontal's terrible. This is asking for disaster. Orientation-wise, this is a reasonable design, vertically upward. This one, you got stratification happening in here, and I'm a bit leery of this. Going back up here, you should also look at this point right here. The dry out point, as goes by the various names. Dry out point, burn. Dry out means it's no longer wet. Burnout, it's often called burnout point. And it happens right here, except it doesn't happen right here. This liquid film is going to be bouncing around. But if you take a look, there's a huge temperature change here. The wall temperature undergoes a drastic change. Now, since this film is not exactly fixed at one location, it will bounce around a little bit. This temperature change will bounce around, become a little bit fuzzy. But there's a lot of thermal stresses happening here, right along here. And this is where you can have fatigue wear, basically. The metal becomes fatigued because it's undergoing very high temperatures and then drops down low temperature, high temperature, low temperature, high temperature, low temperature, high temperature, low temperature. It fatigues. So I got another experiment for you to do. I want you to take a paper clip and bend it back and forth and break it apart. I want you to look at it while you do it. And what you'll do is you'll put a lot of tiny cracks in the paper clip. The metal will turn white, somewhat white, due to the presence of the cracks, right? Crack formation inside the paper clip. Now that's what's happening right here. This burnout region, due to the fact that the temperature is fluctuating about, you're thermal stressing this tube. Now, that's a point of tube failure as well. So you come in with your fiber optic camera tube and looking around. You look around, nothing, 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 nothing. And the crack, tube crack would be right there. So this is the region you have for inspection. For a heat exchanger, boiling tube heat exchanger, you want it to be very focused on that one point. Of course, there's a lot of things you want to look at, but that one in particular is... Do you believe that? There's a lot of strange stuff. Now, what the problem is when I get over here to this horizontal flow, I don't have necessarily a fixed point where that's going to happen at. So my thermal stresses would probably be spread out over a larger length of pipe, and also be probably spread out over a larger region along the top, and maybe the tube dry out might be at one fixed point right here, but even that will move around a lot. So horizontal pipes will be less, I would predict, the less are not as thermally stressed as the other pipes are, as the vertical pipes. So there's a big difference between horizontal pipes and vertical pipes. Horizontal, as an engineer, you need to pay attention to the orientation of stuff, right? Now this is about the coolest thing I've ever seen. This is a double boiler heat exchanger, right? First off, we got to realize that up here we got pipe wall here with double pipe heat exchanger, what it is. So you have a wall here, and then you have the annulus volume, and then you have a pipe on the outside sitting there. So you have a pipe inside of a pipe, creating an annulus in here. So the steam is coming in and condensing. So it's condensing all along here, right? Fills up the film condensation, and it's pictured over here as well. And then inside here, this steam coming in, you have liquid freon sitting there going to a vaporous freon sitting there. So you're boiling off your freon. Maybe you have some comments about the boiling oil. And over here you have the different things about flow regimes. Two single-phase flow, two-phase flow water, single phase of Freon, two-phase water. And what do we got? Subcooled phase Freon. Anyway. Kind of a very cool system. Moving right along here, you have flow regime maps. You have various parameters here, various parameters here, and you got different types of flow regime maps. This is great to know that these things exist. I wouldn't trust any of them, right? They're not to be trusted, right? Two-phase flow is real tough. Tough. Multi-phase flow, that means more than two phases, right? Or two-phase flow could be multi-phase if you want it. And you'll quickly find out that it's a tough area to get into because you got all kinds of very strange flow behaviors. Lots of orientation effects. What you want to pay attention to is the vertical siphon and the horizontal siphon. Thermosiphon, there you go. The old type, I don't know. Internal bundle, boy, that's a mistake. You got the kettle reboiler, got the weir, U-tube, baffle plates. You got the liquid level determined by this weir. So you don't have a loop seal, you have a weir in there. Comes in, vapor leaves. Comes in as a liquid, boils, and leaves as a vapor. What you don't want to do is have too much heat in here where the liquid drops. It's very easy, perhaps, to have a liquid down here. And that would mean that half the tubes are in the vapor space. That ain't good. That ain't good. That ain't good operation. It's not good. Heating fluid coming in and leaving. So on a control situation, you want to have this liquid height maintained. Now you maintain that liquid height, in fact you wouldn't mind having a little spillover, is by regulating the flow of the heating element, heating fluid. Now this is a ridiculous unit, ridiculous design, because when I remove this I shut down the entire column. So this is not such a great idea. Necessarily. See, what can happen over here is I could possibly have a couple control valves to take this unit offline to clean it and then bring on another unit over here. And as a result, I don't shut down the distillation column. Over here, when I yank that unit, when I yank this out, the column has to come down. Up here, with this design, yeah, I take this offline, but I could potentially plumb in another heater here. But even to get this thing out, going back to this other one design, even to remove this thing, I have to have no liquid in this region here. All right. So anyway. Special service, there you go. You got all kinds of heat exchangers out there. And you have a lot of, how can I say it? You got a lot of wackos out there. You know wackos? People running around with really great, sensational, change the world type of ideas. And the world tends to change slowly. Even everybody who owns a cell phone, it took them a while to learn how a cell phone is used. Right. So we have cartridge heat exchangers. And what's really funny is static mixers. Now, my original area of expertise was in mixing. So I was talking to a guy about static mixers, and he didn't really want to talk to me, trying to squeeze some stuff out. And then I told him I taught heat exchanger design. His attitude towards me changed. Bam! I was his best friend from long back. I went from a nobody to his best friend long back. Couldn't get enough of me. Because what he wants me to do is sell a whole bunch of static mixers. You realize how many static mixers can go in a shell and tube heat exchanger? Like there's 300 tubes in the exchanger, and they're 16 feet long, and each static mixer is maybe 16 or 6 inches, so they're stacked in there. I'll tell you. There's a picture of a static mixer right there, 1976. And static mixers are actually very wonderful. What happens, it's the device, it's a pressure drop device. Requires a pressure drop to do this. Where a pressure drop requires you to pay a utility bill, right? Because the pressure drop times volumetric flow rate is power, and we're going to pay a power bill on our heat exchanger. But what it does, it knocks heat transfer and everything you learned about heat transfer right in the teeth here. Because it takes the hot fluid along the wall, maybe you're heating the fluid, takes the hot fluid along the wall, puts it in the center line. Or maybe you're cooling the thing, so it takes the cooling liquid and puts it in the center line. Then this fluid has not been affected at all. It's going down the center of the pipe. Suddenly it's along the wall. Okay. So you want the stuff that's not affected to be affected, and you wanted to affect it at the wall. So what was at the wall is now at the center line, and what was in the center line is at the wall. So you get good heat transfer, excellent heat transfer. So when I told him I was teaching heat exchanger design, and I may have 30 people in the audience, which I've done, and actually this is the remnants of the short course. You know, when I was younger, I could talk 5 days on heat exchangers, 8 hours a day for 5 days. No, actually not. It's 7 hours a day. For 5 days, that's 35 hours of continuous heat exchanger talk. I'll tell you, it puts a lot of hair on the brain. Anyway, he really loved me ever since. I mean that in a figurative manner. And so he could sell a lot of static mixers, and that's what he was wanting to do. Besides disrupting the flow field in here and taking fluid at the wall, put it in the center line, and the center line fluid, put it at the wall, there's a slight component of conduction going on here. This is usually made of metal. And metal is excellent in conducting heat as well, whether you're cooling or heating. The other device that's very useful is you take a pipe and fill it up with metal spheres, right? And metal spheres contacting metal spheres, got a whole bunch of metal spheres packing up this tube. That's also a very excellent way of doing heat transfer, if heat transfer is what you're wanting. Static mixers is a great idea. Right. This thing's copyrighted. Actually, no, this thing's stolen. Okay. The how can I tell you the truth, huh? Static mixers have been around about 1901. So right now it's 7. So by the time this thing was printed, static mixers been around for 75 years. The first static mixer was chains. They would put chains in pipes and weld them in, basically. And the chains would be flopping around. They'd be having one fixed point, and the rest of the chain would be able to move around, flop around, which would be helpful if you're trying to disrupt the flow. And so the first static mixer was chains welded inside pipes. Great idea. Works wonderful. Can I buy that? Yeah, I can buy that. Go down and get yourself your pipe. Go to the grocery store and get some chains about the size. Well, not hardware store. Get yourself your chains that would fit inside your pipe. Buy a big length of chain. Weld the sucker in there at some local machine shop, and you got a sensational static mixer. It means that you don't have to wait 6 months. You don't have to go through any design phases. You know it's going to improve things. You just don't know how much is it going to improve things. And away you go. The expense is extremely cheap, right? So, how can I say this? Lots of things can be done quickly, cheaply, highly effective designs without much engineering. And quite frankly, it takes a lot of, how can I say it, common sense to recognize such things can be quite simple. Well, where's the NIST? NIST, you got that? Where's the NIST standards for that static mixer? Well, I don't have one, sir. Well, how can you actually use it if you don't have a standard? It works. NIST, you know what that is? National Institute of Science and Technology. Used to be the old, what is it, Bureau of Standards? National Bureau of Standards. MBS, was it? Anyway, interesting how things work. Now, pinch. See, you got a lot of, if you got a large facility, or say you have a space shuttle, where some stuff you're heating up and some stuff you're cooling down. Now, you can make those two streams. If you need to heat something out and cool something down, you put those two streams together in a heat exchanger, and it's wonderful efficiencies. You don't heat it up separately, and you don't cool it down separately. You line up the two streams, one you want colder and the other one you want hotter, and you set up a heat exchanger between them. And that's what these guys did. There's a bunch of British chaps. They call it pinch technology. I don't know why it's called. Actually, I do know why. There's a pinch in their curve. The curve comes to a pinch point, and if you plot all this stuff up and read their work, this hit, if you take a look, this hit the U.S. industry about 1980s. 1990s, and analysis of heat exchanger networks, significant energy change savings. It's mysterious or mystic. No clearly written discussion of the techniques. I suspect what it is, it's sufficiently disorganized that considering the options you can make, it probably never gets handled very well. Well, when I wrote these set of notes up, there was something called BJAC, right, which is the Bell Delaware method. And that's the one that got et up by, this is the one that's become a computer package. This is the Bell Delaware method. By the way, I should explain Bell Delaware method. University of Delaware after World War II, that's 1945 for those of you who are not good at history. After World War II, University of Delaware, with a consortium of companies, DuPont, Dow Chemical, Union Carbide, various companies decided to study heat exchangers. And so they set up research inside the University of Delaware to carry out this. And over a period, say 1995 to 1960, they produced a large number of PhDs in chemical engineering trying to figure out how the hell a shell and tube heat exchanger worked. Okay, and that got written up in all kinds of dissertations at the University of Delaware. Do you hear the silence? You know what happens to PhD dissertations? Nothing happens to PhD dissertations. They grow dust in some sort of university library and are not implemented, right? So along comes Bell. Now, who in the devil is Bell? Well, he was a professor at the University of Oklahoma. Never met the gentleman. Don't know much about him. But he decides, there's a whole bunch of work that's done at the University of Delaware on heat exchangers. Heat exchangers are, important. Nobody's ever brought this stuff to the technical literature, and it's not being used to design heat exchangers. So he said his last, part of his life, bringing out the Delaware method for the design of heat exchangers. And for his efforts, they now call the method the Bell-Delaware method. Not just Delaware method, Bell-Delaware method. Okay, got it? Now Delaware, University of Delaware Chemical Engineering Department was kingpin. You don't get any higher, you don't get any meaner than the University of Delaware. And I do mean high, and I do mean mean. These guys are not to be played with, and they were a serious bunch of chemical engineers. So, yeah, the Delaware method. Anyway. Oh, look at what we have here. Installation, startup, operation, shutdown, and maintenance and codes. Simple. This is going to feed off of Yodel book and also feed off of Gupta's book, okay? No, it's not going to talk about the Bell-Delaware method. Again, it took me about a month, 30 days. I timed myself, see how long it would take me to get the report on Bell-Delaware and teach me the method. I taught myself, right? Good stuff. Put me to sleep. There was one damn correction factor after another damn correction factor after another damn correction factor. It was a painful experience, and every one of those damn correction factors had the procedure on how to obtain it. Anyway, let's go through some of the more important things in the design checklist and bid evaluations. Required HTC capacity and pressure drop, upper and lower requirements, right? Pressure drop, remember, pressure drop times volumetric flow rates, power consumption. So this is an energy analysis of your heat exchanger. No dead zones, vents, drainage, safety valves. What the devil is safety valves? No hot spots, easy inspection, easy cleaning, easy repair. The vendor reliable. Are you expecting people in business actually to be reliable? Well, there's a chance that they can't deliver. Reputation, what's their reputation? You have a vibration analysis, what's the delivery time, and what's the cost here, okay? So you go to Yodel, this is Gupta's book, anything section 14. Needs of a successful heat exchanger, there you go. Some causes why heat exchangers fail to perform. It's also why. Gupta's book. See, Yodel's book, I don't think, gets up to chapter 14, right? Installation, well, adequate foundation piping installed horizontally, easy replacement when it's done. Sufficient maintenance space to remove tube bundle, cranes for headroom, sufficient space to remove heat exchanger. You might do a scale model, piping allow bypassing the streams for easy and for inspection and maintenance. Piping for backflushing. purge chambers, instrument alarms, appropriate lifting lugs. Wouldn't it be funny if you built a heat exchanger you couldn't lift it? You want to lift the tube bundle by the baffles. Right? If you lift the tube bundle by putting straps under the tubes, then you should be shot at sunrise. Right? You lift the tube bundle by the baffles and also the tube sheet. If you put a lifting strap around the tubes, you should be shot at sunrise. Right? Adequate drainage, so that one can tell when the heat exchanger is drained. Check for shipping damage, tightness of channel covers. Remove all preservative materials and dry exchanger. Remove shipping and foreign materials. Make unforced piping connections. That's very important. Forced piping connections, you're forcing two pipes together. When you undo those, they'll spring back. And when they spring back, they could hit you in the chest and you die. So you better be careful. You don't want to make any forced piping connections. And if you do make unforced piping connections, then you don't necessarily want to be around for when they are decoupled, because again, things may have changed on you. Supports should allow for thermal expansion. Rollers and V-slots. Pressure test your exchanger. Install the exchanger and seal. Seal installation. Make sure everything has a hook on it. Restrictions to small diameter shells, floor space, and layout. Serving and pushing in and out of the tubes. Commissioning a heat exchanger. Startup. Things you need to start. Maybe better than you expected. You've got to be careful. If you are operating better than expected, it could cause problems downstream. Bypass stream may be necessary until the exchanger fouls to design. That's the other thing. The exchanger fouls to design. It doesn't foul anymore. Take your car. It says to flush your radiators every year to put in new fluid. Now, I'm not quite sure you want to do that. Your car radiator is a heat exchanger. And basically what will happen, it will foul. It'll foul to a certain level, after which your fluid is doesn't have any more, radiator fluid doesn't have any more fouling agents in it. In a sense, it's all fouled out. So you fouled to design, and you don't have to worry about fouling afterwards. Now you come along and they say, well, you need to change your radiator fluid every year. So now every year you put in new material which has to foul. So by servicing your radiator, you're actually perhaps building up a level of fouling in there, which may then be a real problem. Startup may require low flow rates. Bypass stream may require a mixer. Keep temperature below, keep pressure low until metal temperature is above the transition temperature, so you don't have any brittle failure. Apparently at low temperatures, metals tend to be brittle, and they could possibly crack on you. Shut down, all kinds of problems. Section 1411 in Gupta's book's really wonderful. Reduce flow hot fluids gradually. Then cool quickly. Well, avoid line freezing, line crystallization, drain the heat exchanger. Give you a hint. I asked you a long time ago, why do you notch the baffles? You got to watch out what I just said. That was wrong, Tatterson. Why do I notch the baffles? No, that's not really what was there, Tatterson. You got to look in the back of what was there. The notch was at the bottom of the baffle, right? So now the question becomes, why do you have to notch the baffle at the bottom? Now that's the question, right? The next question is, what similarity is there? How is a heat exchanger, shell and tube heat exchanger, similar to your bathtub? Right. And so now you know why you have to notch your baffles, right? Let's think a little bit. You drain your heat exchanger. Maybe you're going to open it up, put in some anti-vibration items on your tubes. So you're going to have to drain your heat exchanger. How do you drain your bathtub? Or for that matter, how's your bathtub drained? So there you go. So what similarity? There's two similarities that have to be done here. You got to drain your heat exchanger. You got to drain your bathtub. So what are the two similarities involved? There's two things you want to have similar here. I'm drawing an analogy between bathtubs and shell and tube heat exchangers. Let you try to think about what you're doing. You do know what a bath is, right? A bathtub. You're not a shower person all the time, are you? Anyway. Checklists, baffle breakage, tube ruptures, tube sheets can break, flanges can break, seals, tube rupture. How do you monitor tube rupture? Well, you're always checking the exit streams of your heat exchanger. The rupture of a tube will be detected by a composition change in your exit streams, right? That way you know whether you have a tube rupture or not. The leak will go one way, right? The leak will be determined by the pressures, right? It's either leaking in or leaking out of the tube, right? You got to worry about proper drainage of the condensate. Collected condensate can cause drop reduction in heat, water hammer. That's the one thing I'd like to know more about is water hammer. I think it's one word. Sometimes it's two. Periodic maintenance. If not done, long downtimes will occur. Extremes in operations. So there you go. Some things of concern in the operation of a heat exchanger. Operations before tube rupture. Rattling noise in the exchanger. Leakage increases. Heat transfer, pressure drop, material cross-contaminates, sample streams for contamination. There you go. Leakage in tube sheets, well, not a great idea, can cause process problems. Alternative, use double tube sheets. Movement of baffles can be a problem. They are held in place by tie rods. If loose, baffles may walk on you. Extremes in operation, well, you got heat load, got very high heat load, maximum fouling, maximum cooling, all kinds of nasty stuff going on there. Don't want the streams to freeze, boil, or run dry, or maybe run full. Minimum heat load, clean tubes, coldest fluid temperatures. Extremes in operations, so you should try to avoid. It's really funny, a story. A feed tank up in Cincinnati, Ohio. It was essentially a large water tank. And it's a large water tank, and basically they used it as a water feed to their process. So one day they got there, and the very cold night where the temperatures dropped below 32 degrees Fahrenheit. And what happened is the entire tank froze up on them. So when they went to get the water feed they needed for their process, the water was all frozen, and voila. They forgot to put a heater in the storage tank. Oh, mamma mia, Colucci. There you go. Forgot to put a heater in the feed tank. Don't want the streams to freeze. There you go. Prime example. That was Procter & Gamble, Cincinnati, Ohio. It's also one of our students was in charge. And they forgot that water freezes. I guess they never seen an ice cube before. Huh? Anyway, just kidding. That would be terrible to have a reboiler going dry Remember I was talking about the reboiler where the liquid level drops below the tubes? That ain't a healthy way of operating. Accessibility of the heat surfaces. You want to clean or inspect. Heat exchanger tube bundle can be removed. Requires space for tube bundle length. There you go. Maintenance. Oh, this is a really fantastic set of statements here. Maintenance should begin at the design stage. Got it? Maintenance should begin at the design stage. Maintenance should be built into the design. You want to make maintenance easy and have the maintenance people work with the designers, manufacturers, construction during erection. Right. Now, the maintenance people, they're the dummies, right? No, not necessarily. Maintenance can be have a lot of smart people there. They may not be paid well, and they may not have respect from everybody else, but you need to pay attention to maintenance people. I always like to bring the operators, maintenance people, operators. You always want to bring them coffee and donuts. You know what I mean? Look at me. I bring donuts to classes, dozens of donuts to my students. Same sort of thing. There's a significant human aspect that you need to pay attention to get information. You see, the third shift, if you bring coffee and donuts for the third shift, you know, the graveyard shift, around 3 or 4 a.m. in the morning, you bring them coffee and donuts, sit down, talk with them. They'll tell you all the things that the first two shifts are doing wrong. See, they'll tell you the first shift is doing this wrong, the second shift is doing that wrong, and so you got a whole bunch of information, just from using your personal skills. What contributes to poor maintenance, this is often a test question as well. First problem is non-planning of maintenance. Maintenance jobs are not analyzed. Breakdowns are not accurately documented. Spare parts and tools are not available. There you go. That's typically what happens to me. I have a job around the house. I don't have the tools, nor do I necessarily have the parts. Combination of the operations and maintenance. Basically, operations want to run the equipment. Maintenance probably wants to protect the equipment. So you got natural conflict between the users and the maintainers. So the coordination between these two groups may not be as pleasant as you would like them to be. Find out the important mechanisms, evaluate the vendor equipment, evaluate maintenance, analyze the frequency of problems, develop a maintenance schedule. All right. And service inspections. Many items are not accessible. In other words, you need to get into your heat exchanger to see what's going on. Assess serviceability of the heat exchanger. Inspect welds and expansion bellows. Defects in welds can take time to develop. Having tried to become a welder myself, there is an awful lot of metallurgy that goes into welding. I did not want to learn metallurgy, so I failed at welding. And the other thing the guy was keep on telling me, this is what he was saying. He says, welding's is a young man's occupation. This was about 5 years ago. 8 years ago, I wanted to become a welder. And I was, 60? And the old man was younger than I am, or about the same age, the teacher, I guess. And he always would say, welding's for young people. He'd say that. 10 minutes later, he's saying the same damn thing. So I eventually caught on to what he's saying. He was telling me to get the hell out. Too damn old. Like I said, you wouldn't want to have me as a welder. And what's interesting about welding, and what really made me decide to stop my efforts, was sometimes you have to weld above your body. And it is possible for the hot metal to drop down into your upper chest area, can drop down through your collar and upper chest area, so you got something hot going down your torso there. I thought that maybe I should give it up. So welding, where you're looking down at it, is okay. But when you're welding something that's over your head, that's not necessarily what I would consider something that I really wanted to do. Anyway, welding is damn difficult. If you're a good welder, you can probably make a lot of money, but not as much as a regular type, sit back in the chair, drinking coffee type engineer. Troubleshooting areas. Well, temperature extremes are always a problem. Affects operation. Process myths may result. Has there been any major flow regime changes? That would be line freezing, boil off, running dry. Little fluid information at extremes. Now you got to recognize when you're doing scrambled eggs in the morning and you scorch your scrambled eggs, you've reached fluid properties at the extreme. You don't want to scorch your scrambled eggs. Jeez, oh man. Fouling. Can you predict or reduce a multi-phase prediction of pressure drop flow regimes? Like I said, multi-phase is tough. So you have all kinds of things that can happen to you. Line freezing, caking, plugging, coking, plugging, all kinds of things. Multi-phase flow, possibly causing flow vibrations or tube vibrations. Corrosion points are typically possible between the baffle and the tube, or the tube and the tube sheet. By the way, I should point out, what do you do with a tube that's leaking? Well, the hard way is pull the bundle and replace the tube. And some of these designs you can replace the tube. At least that's what they say you can. But stop to think about it. You're replacing the tube that's 2 or 3 tubes in, right? Replacing an outer tube might be easy. But replacing a tube that's 2 or 3 tubes in, now there's the rub. I don't know if that would be easy. So when you have a tube that's got a leak in it, a smart thing to do is just plug it. Put a big old plug in it, both ends, right? And that will prevent your problem with leaky tubes. Then after having done that, you plot the number of tubes that have been plugged with time. And hopefully you won't have a problem. You just have a fairly linear failure rate on tubes. Except when you don't have a linear relationship of tube failure with time. The number of tube failures goes exponential as a function of time. You want to take down the whole exchanger and pull the bundle and get a new bundle and put it in. Got it? You should perhaps, if you're really conscientious, you probably already have a tube bundle made up for you, right? You may want to have a tube bundle ready for insertion. That's if you had a lot of money and was worried about downtime. Stop to think about tube bundle, maybe $40,000, $70,000. I mean, well, let's retract that. I'm not sure. I was talking about the heat exchanger being $1 million. So, okay. Say it's $1 million. Say the tube bundle will buy you a tube bundle, new tube bundle is $400,000. Okay. And your plant is making $100,000 a day. So you're making $100,000 a day, maybe $50,000 a day. So in 8 days at $50,000 a day, you have essentially equaled the purchase of that tube bundle. So the question is, do you risk downtime, which can be extremely expensive, as opposed to a tube bundle, which is also expensive? In which case, depends upon your experience, your attitude, and whether you really want to withstand a 2-week downtime in your plant that's making $50K a day, right? You do know how much you're making a day, don't you? Don't you think you ought to find out? I know NASA don't make no money per day, but do they? They often have burn rates, but us out there in the world of engineering, we have, that's what a chemical plant is, basically. A plant is, excuse me here, I have a phone here I got to answer. Notice how I use my cell phone. There, it's off. Didn't answer. Never answer your cell phone if it's going to be an advertisement. Anyway, you're working in a plant, you should know how much money you're making per day and weigh that against how much downtime is going to cost you as a cost of equipment failure. Poorly designed reboiler, it switches from film boiling to pool boiling. Film boiling is not very good. Film boiling is bad news. Pool boiling, I got to figure out what the devil that is again. But you don't want to have vapor lock. You don't want to have a vapor surrounding your tube bundle. That's called vapor lock, right? And you don't want film boiling for sure. That's bad news. Codes and standards. There you go. There you go. There's all kinds of codes and standards out there. We already talked about TEMA standards. And American Petroleum Institute has standards, and ASME has standards. And what are those? They're codes, rules and recommendations for material selection, design, fabrication, operation, testing, and inspection. Set the minimum standards to ensure safe operation and design conditions. There you go. Codes and standards are made legal documents only by the legislature. Whatever, who they are, whatever government's hanging around, sucking tax money out of us, right? So there are only standards there. Most popular is ASME. And the written codes themselves could be 32 feet long. Right, book after book after book after book, and quite frankly, in some jobs you're not any good unless you know the standards. Oh Lordy, we got to do one of these things again. There you go. So we have the TEMA, Expansion Joint Manufacturers, American Society of Testing. I don't know how many of these are still existing due to the fact that maybe we shipped everything to China. Let's see what we got here. Oh. Look at that. I made a success here. Purpose of codes: provide adequate safety under most circumstances. However, does not take into account all possible conditions that might be encountered. And ASME codes cover new construction. However, what is not covered? Well, lots of things that are abnormal are not covered. In other words, unusual temperature extremes, low temperature or high temperatures, unusual thermal cycling and stresses, very high pressures, local hotspots, obviously explosions and runaways, unusual vibrations and unusual attacks. So there are codes do not cover abnormal situations. Does not take into account all possible situations. That means codes are limited. Okay, here's the ASME codes. Ferrous metals, non-ferrous, power boilers all by themselves. Then you go through welding rods, electrodes, filler metals. Then you have all kinds of things. Heating boilers, non-destructive examination, and then pressure vessels, welding, abrasion, whatnot. So I'm sure that there's a lot more to ASME codes than just this. There are 11 sections, they say. I bet there may be more than that nowadays. I'm not sure. Oh, yeah, rules for in-service inspection of nuclear power plant components. That right there is a room full of codes. Now they're put on discs, so maybe only a couple discs or maybe just one stick. General requirements, methods of fabrication, materials, mandatory details of procedures, non-mandatory information suggesting procedures. Uh-oh, what am I happening here? Oh, okay. General requirements, material, design, fabrication, pressure relief. Very important, pressure relief. Inspection, radiography, testing, marking, stamping. Here you go in and you take x-rays, right? And look at welds. You remember the big scandal about the Alaska pipeline and how like almost every weld was bad in the Alaskan pipeline? Anyway. Oh, jeez. ASME definitions given for design pressure, temperatures, allowable working pressure, operating temperature, pressure, thicknesses. Shells up to 63. I don't know if that's true or not anymore either. I have to go ask TEMA. Tubular Exchanger Manufacturers Association. Nomenclature, fabrication, general fabrication, performance, installation, operation, maintenance, mechanical standards, material specs, thermal standards, physical properties, general information, recommended good practice. TEMA has R, C, and B. Classifications of heat exchangers, recommended good practice. Broad topics of the American Petroleum Institute. General suggestions, proposals, drawings, guarantees, design, materials, fabrication, inspection, shipment, and supplementary. Anyway, so I'm going to quit here, and sorry about our rough startup. I don't know if it's even been recorded, but I'm stopping at page 31 on the third set of notes, so we can pick that up in class. Again, this is lecture 2. This is for July 3rd, Monday of July 3rd, which is a school day, which means you should be in class, but we know that your attendance will be poor. So I'm sending this out on video to you, right? And in class, we'll begin with fouling, erosion, corrosion, and flow-induced vibrations. By the way, this is a summary of a course that I taught through the University of Wisconsin for maybe 5 years. And obviously this is a reduction of, that course was 5 days long, 7 hours a day. This course is, this part in here is 4 hours, maybe 4.5, 5 hours, which means there's a whole bunch of stuff that's not included here. Thought I'd tell you that. Okay. You all have a good holiday, and my battery's low. Jeez, oh man, what do I got down here? My battery. I only got 32 minutes left. Well, enjoy your 4th of July. I hope you have a safe 4th. I hope you come back all in one piece. And again, you want to stay away from those explosions. Yeah, they can be a life-changing situation there. Have a good day. Bye. Okay, I'm done. Thank you very much.
No problem.